Hey there, period 7 students. I'm sorry that I am not synchronous with you today. I really wish I could be there. However, I did have to make a doctor's appointment and the only available appointment fell during your class, so I do apologize for that. What I'm going to ask you guys to do today is to watch this video along with completing a Pear Deck. So the Pear Deck code is BHU CTQ. It's in the upper corner of my screen. I'm circling it right now. And there's going to be times where I ask you guys to pause and to complete the work in the Pear Deck, as well as just to make sure that you are taking notes for yourself. This is in lieu of our lesson. This is what I did with all of the other classes today. So just make sure that you guys are taking notes. So we are jumping into our next unit, which is going to be all about compounds and why atoms really form compounds. And specifically, we're going to focus on neutral compounds. That's really the only type that exists. And so let's go ahead and jump forward. So this is our first pause moment. Okay, before I go through and talk about the answer to this, please pause and try this. So on the count of 3, hit that pause button and draw the Bohr diagram for sodium. Okay, 1, 2, 3. Okay, hopefully you paused and now you're unpausing, but I'm going to go ahead and just go over this quickly with you. So let me go ahead and share my student screen now, and I'll start to draw on that for you. So the first thing that we want to do is we want to make sure that we have our stuff in our nucleus. So sodium is element number 11. So we would have 11 protons in our center, and we have a mass of 23, so we would have 12 neutrons in our center as well. And next we would need to include our valence electron, or all of our electrons, I'm sorry. So the electron configuration for sodium is 2-8-1. Okay, and so looking at that, we are going to have 2 electrons in our first energy level, and then we're going to have 8 electrons, 5, 6, 7, 8 in our second energy level, and then we are going to have just the 1 valence electron in the third energy level. Now, something to note about sodium, remember that sodium is classified as a metal, right? So if it's classified as a metal, that means that it is going to lose electrons. And again, the reason it loses electrons is because it has low ionization energy and low electronegativity. So it doesn't require that much energy to take the electron away, and it has very, very little attraction to electrons. And so therefore, this valence electron on the outside will go away, okay? Now, something that I do want to note for this is I want to note that the valence electron, when we lose this, remember that the ion that we form is smaller than the atom, okay? And that is really what we're going to be mostly interested in this unit, is going to be the ion formation, not the atoms as much, because again, when we're talking about forming bonds, we're typically going to be talking about ions. So it's going to be smaller than the atom. It loses that full valence shell. The atomic radius was this, but our ionic radius in blue is now just going to be this, so it is going to be smaller, okay? Now, drawing Bohr diagrams is super tedious. It's really not necessary for this unit, because while it is helpful for us to visualize the atom, again, we're really only interested in ions. And because of that interest in the ions, we're going to talk about a new way to go ahead and draw those atoms, okay? So let's go ahead and skip to our next slide. How do we define the octet rule? So I want you to go ahead at this moment. I want you guys to pause, check your own understanding. How do we define the octet rule? So on the count of 3, hit that pause button. 1, 2, and 3. All right, excellent. So hopefully you guys have paused, and let's go ahead and take a look at the answer. So remember, the octet rule is all atoms strive to achieve a full valence shell like the noble gases, okay, and which hold 8 valence electrons. Valence electrons, okay? There are some exceptions. So the exceptions, we say fall under what's called the duet rule, okay? The duet rule is going to be the idea that atoms like H, He, Be, or I'm sorry, Li, and beryllium, okay, want 2 valence electrons, or they're striving for a full first energy level, which again, remember, can only hold a maximum of 2 electrons. So hydrogen might gain 1 electron, helium is already stable, lithium will lose 1, and beryllium would lose 2, just to get to that full first energy level. Okay, so hopefully you guys already are familiar with octet rule. Again, it's going to become important because as we move forward talking about ions, we want to know whether atoms are going to gain or lose and how many they're going to gain or lose to get to that full valence shell. Okay, so let's go ahead and move forward. So I want to go ahead now and talk a little bit about the Lewis dot diagrams. So I'm going to go ahead and actually pull up. I'm trying to think about the best way to do this because I can't annotate without it being a drawing slide. So let me see. Can I do just this? No. So, all right, everybody, I'm going to pause this and pull something up. I'm going to pause my recording and just pull something up while I am here. So let me go ahead and find my recorder. Let me pause that quick. Okay, cool. Thanks for bearing with me, everybody. Technological things, got to figure them out. So now let's talk a little bit about Lewis dot diagrams. So now that it's not on my screen share, like the definition, you should have your Pear Deck open, but it's the idea that representation, it's going to be a new way to represent an atom. Like I said, Bohr diagrams are really not that important to us at this point. We're really only interested in valence electrons when we're going to be talking about formation of ions and bonding. So the Lewis dot diagrams are the representation of an atom or an ion that utilizes dots to symbolize valence electrons. So on your screens, on your Pear Decks, you guys will see that I have 2 letters there. I have an X and I have an O. Okay, and so I want to go ahead and I want to show you guys how to draw those Lewis dot diagrams. Now I'm going to start with oxygen, so just watch as I do it first and then take notes. So when you are drawing these Lewis dot diagrams, there is a specific way that the electrons fill in. So we start up top. So we have our first, let me just first state oxygen has 6 valence electrons. Okay, and so that's the piece of information. How do I know that? I can use my periodic table to look up the number of valence electrons. It has 6. Okay, so the first electron goes in the upper left, followed by the second in the upper right. So the first 2 electrons get paired up top. Then we have an electron here to the right-hand side, then an electron to the bottom, then an electron to the left. So we basically loop around clockwise, and then we are going to loop back around clockwise for our 6th electron. Okay, and without getting too in depth in this, again, remember that day that we kind of talked about orbitals and s, p, d, f, and filling, and something you guys don't need to know for this course, but that's why the electrons fill this way. It has to do with lower energy levels, and so we do have to draw them that way, but without going into too deep of explanation, just it is what it is. Okay, so let's use X to represent any atom. Okay, so just think of it, this is just X, meaning this could be literally anything. But here's the way the electrons fill. Here's going to be your general formula. Again, number 1 goes upper left. Number 2 goes upper right. Number 3 goes on the right. Number 4 at the bottom. Number 5 to the left. Okay, number 6 goes under 3. Number 7 next to number 4. And number 8 next to number 5. Somebody in my earlier class said, well, what if it's, something that has 2 letters? That's okay. Just spread your electrons out across the top like that. Okay, so now what we're going to do is we are going to go ahead And let me just minimize this real quick. Okay, and we are going to go ahead and move on to some practice. So what I want you guys to do is draw the Lewis dot diagrams of these electrons or of these atoms, okay, sodium, magnesium, aluminum, phosphorus, and chlorine. Okay, and I want you guys to go ahead and draw those on. So in 3 seconds, you're going to pause. Ready? 1, 2, 3, pause. Now, hopefully you've paused, and we're going to go over the answers. So again, I think it helps to think about the number of valence electrons ahead of time that each one has. So sodium has 1 valence electron. Magnesium has 2 valence electrons. Okay, aluminum has 3 valence electrons. Phosphorus has 5 valence electrons. And chlorine has 7 valence electrons. So sodium, we are going to have just the 1 valence electron up top. Magnesium, we're going to have 2 valence electrons up top. Okay. Aluminum, we're going to have 1, 2, and then our third one, I'm sorry, that disregard that dot on the bottom. I keep accidentally clicking. Okay, let me erase it actually so it's not going to confuse anybody. There we go. Okay, now for phosphorus, we need 5. So again, 1 up top. Okay, 2. So annoying. Okay, 3, 4, and then 5. And then for chlorine, we need 7. So the first 2 pair. Then we go to the sides, 3, 4, 5. Okay, then we loop back around, 6 and 7. Okay, so those are going to be our Lewis dot diagrams of atoms. Now let's talk quickly about ions. Okay, so let me go ahead and we are going to skip to the next slide. Actually, before we talk about drawing the ions, let's talk about fulfilling the octet rule. So again, in order to fulfill the octet rule, let me go ahead and I'm just going to type it here. It's not going to be big, but just, you know, this is review. So remember we said metals lose valence electrons in order to form an ion, and non-metals will gain valence electrons in order to form the ion. Okay, cool. Sorry, you should have paused and did that, but oops. Okay, let's go ahead and move forward. Last slide, drawing Lewis dot diagrams for ions. So I wanted to take notes on this, and in class I would, but again, I'm going to use that blank PDF that I just created. So give me just one moment and let me find that. Okay, here we go. So let's go ahead and talk about this. So again, let's talk about drawing the dot diagrams for ions. So let's first start with magnesium. Okay, so again, the magnesium atom has 2 valence electrons, okay, and it has a neutral, overall neutral charge, okay, and we know that because we know that it has equal protons and equal electrons, okay, giving it an overall 0 charge, okay. Now, as an atom, the 2 valence electrons, that's great, but again, it wants to strive for a full valence shell, so it's going to lose electrons. Now, when we lose or gain electrons, we're filling or losing the entire valence shell. So in this instance, we want to lose 2 electrons total, right? Magnesium has an electron configuration, the atom of 282. And so we want to lose 2 electrons to have that full 8 in the valence shell below it, okay? So we're going to lose 2 electrons. Now let's first talk about the charge that forms. So in our magnesium ion, okay, we now have a total of 12 protons. Remember, protons don't change. And we have electrons. We have a total now of 10 electrons. Now, as a result of this, right, remember metals lose electrons and they're going to form positive ions. But here's why. I now have 12 positive charges and only 10 negative charges. So if you think about them balancing each other out, 10 of those negative charges balance out 10 of those positive charges. But that leaves us with an overall extra +2 positive charges, so an overall +2 charge. Now that is important because that now gets written to represent the fact that this is an ion in the upper right-hand corner of that symbol. So I now have Mg +2, And notice how there are no electrons on that now, because it represents the fact that it lost all of those electrons, okay? And again, this upper charge here, this represents the charge that's formed by those electrons being lost, okay? Now let's talk about phosphorus. Okay, so I'm going to go ahead and I'm going to actually erase this because it's taking up too much of my space. If I can get the eraser to work. There we go. Okay, so let me just quickly erase this. And we'll talk about phosphorus. Let me just go ahead and pause this and do this so you guys don't have to watch me erase it. Okay, so we're back. So let's talk about phosphorus. So phosphorus, again, the atom has 5 valence electrons, okay, and an overall 0 charge again, because since it's the atom, it has an equal number of protons and an equal number of electrons, and as a result, an overall 0 charge. Now, phosphorus is a nonmetal, and remember we said nonmetals want to gain electrons. It has 5 valence electrons as it is, but it wants a total of 8, so it needs to gain 3 electrons in order to form its ion. So for the ion, let's just first start with determining the charge. So we have, again, a total of 15 protons, and now we have 18 electrons. And so again, we want to think about the balance. 15 of those positives balance out 15 of those negatives, but I still have 3 additional negative charges, which is going to give me an overall -3 charge. Now, remember for magnesium down here, we looked at the fact that it has 0 electrons in its ion form because it lost those electrons. Well, phosphorus gained electrons. So we need to show now that it had, here's its 5 original electrons, but let's go ahead and show the fact that it gained 1, 2, and 3. So now it has that full 8 valence shell, okay? You do not need to use other colors when you're doing it. I'm showing it for you guys now. Okay, so it gained those 8 electrons, or I'm sorry, it gained 3 to have a total of 8 electrons. And now we need to include the charge. But there is one additional thing on the nonmetal ion that we are required, and that is to give those electrons a little house. Okay, or at least that's what I like to call it. These brackets help us represent that the electrons belong to that phosphorus ion. Okay, and that's going to become very, very important for us for tomorrow's practice, or for our Edpuzzle video for homework tonight. We'll talk about why. But just get in the practice, non-metals require brackets and metals don't. Okay, now last thing we need to do is include that charge. So it forms that -3 charge. And again, that -3 charge comes from down here where we calculate the charge based on the ions. Okay, everybody, again, I'm sorry I wasn't there with you guys today. I hope you guys have a fantastic rest of your day, and I will see you guys tomorrow. Have a great day, guys.